We give it a single name, as if it were a single place. One dot in the southern sky, one destination, one word, Alpha Centauri, the nearest star to our own. But that word is a lie of compression. Hidden inside it are three suns that almost never share the same sky, separated by gulfs so vast that one of them takes 500,000 years just to circle the other two. Inside that one name live a sun like ours, a smaller orange ember beside it, and a faint red coal drifting so far away it was nearly mistaken for a stranger. We say the nearest star system and picture a tidy second solar system. The truth is stranger, emptier, and far larger than the name admits. If reconstructions of how the universe is actually built are the kind of thing you enjoy, take a second to tap that like button and subscribe. It genuinely helps, more than I can say, and I'm grateful you're here. Now, get yourself comfortable. Let's begin. Begin with the two stars that sit at the heart of everything, because the whole misunderstanding starts here. Two suns, locked together, circling a shared point in space the way two skaters circle while holding hands. Astronomers label them simply A and B. One is a yellow star almost exactly like our own, slightly heavier, slightly brighter, carrying about 1.1 times the mass of the Sun and pouring out roughly 1.5 times its light. The other is smaller and cooler, an orange star holding about 9/10 of the Sun's mass and shining with less than half its brightness. Side by side, they would look like a bright golden lamp and a dimmer amber one. They have been turning around each other for billions of years, and they will keep turning long after everything you have ever known has crumbled into dust. But here is the first detail that breaks the simple picture. These two stars do not hold each other at a fixed, comfortable distance. Their orbit is not a tidy circle. It is a stretched ellipse, an egg-shaped path with a measured eccentricity of about 0.52, which in plain terms means the gap between them is constantly breathing, swelling open, then closing in, then swelling open again, across a cycle that takes very nearly 80 years to complete. Think about what that number means. A human being born at the moment the two stars swing closest together could live an entire life. Childhood, work, family, old age, and only near the very end of that life would the stars finish a single lap around each other. One orbit of this pair is almost exactly one long human lifetime. We are not watching a fast little waltz. We are watching something so slow that no single observer in history has ever seen the stars complete a full circuit and return to where they started. Now follow the breathing of that orbit, because the size of it is the first real shock. At their closest approach, the point astronomers call periastron, the two stars come within about 11 astronomical units of each other. One astronomical unit is the distance from the Earth to the Sun, so 11 of those units is roughly the distance from our Sun out to Saturn. Picture that. At their friendliest, their most intimate, these two suns are still held as far apart as the Sun is from the ringed giant in our own sky. And that is the close part of the cycle. As the orbit swings outward toward its far point, called a pastron, the separation stretches all the way to about 36 astronomical units. That is roughly the distance from our Sun out to Pluto, on the cold outer rim of the solar system. So across its 80-year rhythm, the gap between these two stars yawns from a Saturn-sized distance to a Pluto-sized distance and back again. On average, taken across the whole cycle, they sit around 23 astronomical units apart. Let that settle. Even the closer of the two stars never gets near the other in any cozy sense. If you stood on an imaginary world circling the yellow star, the orange companion would never be a second sun overhead filling your sky. It would be a single, fierce point of light far brighter than any planet we see at night, bright enough to cast faint shadows, but still unmistakably a distant star, not a neighbouring sun looming close. The two stars are bound, they are partners, and yet they keep each other at the length of an entire planetary system. We even have names for them, old names, older than telescopes. The yellow star, the larger one, carries the formal name Rigil Centaurus, an Arabic-rooted phrase meaning the foot of the centaur. The orange companion is named Ptolemy. For most of this story, I will simply call them A and B. because the labels matter less than the architecture, and the architecture is this. 2 suns, one golden and one amber, swinging through an 80-year ellipse that opens and closes between Saturn-distance and Pluto-distance. That is the central machine. That is the engine room of the entire system. Everything else orbits the consequences of those 2 stars and their restless, stretching dance. And right here, most people's mental image stops. They imagine this tight pair, picture maybe a planet or 2 threading between them, and file the whole thing away as the nearest star to us, a slightly more crowded version of home. But the pair is only the beginning, because there is a 3rd member of this family, and to find it, you have to leave the 2 bright stars entirely behind and travel outward into the dark for a distance that the human mind genuinely struggles to hold. Its name is Proxima Centauri, and almost everything about it is the opposite of the 2 stars we just met. Where A and B are luminous and sun-like, Proxima is a red dwarf, a small, cool, dim ember of a star, carrying only about 12.5% of the sun's mass. It is so faint that no human eye has ever seen it without a telescope. It was not even discovered until the year 1915 by the astronomer Robert Innes, long after the bright pair had been catalogued and named for centuries. It is a feeble, flickering coal next to 2 roaring furnaces, and it is the single most important clue to how badly the name fools us, because of where it sits. The 2 bright stars, A and B, are separated at most by about 36 astronomical units. Hold that figure. Proxima Centauri is separated from that pair by roughly 13,000 astronomical units. Hear that again slowly. Not 36. 13,000. The distance from the bright binary out to the faint red dwarf is something like 400 times the widest gap that ever opens between A and B themselves. If the 2 sun-like stars represent the lit, crowded downtown of this system, Proxima is not in a distant suburb. It is in another county entirely, sitting alone in the dark, so far out that for a long time, astronomers genuinely could not tell whether it belonged to the family at all, or was merely a stranger passing through the same patch of sky. Let me make that gulf physical, because raw numbers slide off the mind, shrink the whole system down. Imagine the 2 bright stars, A and B, as 2 streetlights standing roughly 1 city block apart, close enough that you could walk from one to the other in a couple of minutes. On that same scale, where does Proxima stand? Not at the end of the street, not across town. On that scale, the faint red star would be sitting more than 30 miles away, glowing alone on the far side of an entirely separate city. 2 lamps a block apart, and a 3rd lamp a half-hour's drive into the distance, and all 3, somehow, part of the same arrangement. That is the true shape of what we casually call one-star system. Here is another way to feel it, using our own solar system as the ruler. The planets of our Sun thin out and end around 30 to 40 astronomical units, out where Neptune and Pluto crawl through the cold. But our Sun's gravitational reach does not stop there. Far beyond the planets lies a vast, sparse shell of icy bodies, the distant comet cloud drifting at thousands of astronomical units from the Sun. Proxima Centauri, at 13,000 astronomical units from its companions, orbits them at a distance comparable to where our own Sun's far-flung comets wander. In other words, the red dwarf sits as far from the bright pair as the loneliest, most distant, frozen members of our own solar system sit from us. It is not orbiting close. It is orbiting out where the cold things drift. That distance translates into time in a way that is almost dizzying. While A and B finish a lap around each other every 80 years, Proxima takes something on the order of 500,000 years to complete a single orbit around the central pair, 500,000 years for one circuit. The last time Proxima was at the same point in its orbit, no modern humans existed yet anywhere on Earth. Our entire species, every civilization, every empire, every word ever written, fits comfortably inside a sliver of one of Proxima's years. The bright stars dance to the rhythm of a human lifetime. The red dwarf moves to the rhythm of an ice age, and then some. So for decades, a real question hung over all of this. Was Proxima actually bound to the other 2, chained by gravity into a single system? Or was it simply a nearby loner that happened, by chance, to be drifting through the same neighbourhood at the same time, soon to wander off again? At 13,000 astronomical units, moving at a crawl, The answer was genuinely hard to pin down. The faint star's motion was so slight and so slow that distinguishing a true orbit from a chance flyby pushed the limits of measurement. The matter was only settled relatively recently. In the year 2017, astronomers finally measured Proxima's tiny velocity and trajectory precisely enough to prove that it is, in fact, gravitationally bound to the bright pair, genuinely orbiting them, genuinely a member of the family, not a passing stranger. The chain is real, even though it is almost unimaginably long and almost unimaginably slack. This is a single system, but it is a single system held together by the faintest imaginable gravitational thread, stretched across a gulf so wide that light itself takes months to cross it. But proving that Proxima is bound to the bright pair only sharpens a deeper and stranger question. One astronomers are still turning over. Was the red dwarf actually born alongside the other two, or did it join them later? It is not a trivial distinction. The most natural assumption is that all three stars condensed together out of a single collapsing cloud of gas, siblings from the same nursery, and have travelled together ever since. If that is true, then Proxima is exactly as old as A and B, and all three of them came into being together at one and the same moment in the distant past. But the alternative is genuinely possible, and it would change the character of the whole system. Proxima may have formed elsewhere, on its own, and only later drifted into the gravitational embrace of the bright pair captured, rather than born into the family. A marriage, in other words, instead of a bloodline. Why is this even in doubt? Because of how loosely Proxima is held, a capture and a shared birth can leave behind very similar arrangements once enough time has passed, and the clues that would tell them apart are subtle: the precise ages of the stars, the exact chemical fingerprints written into their light, the fine details of how Proxima moves. The bright pair's ages and compositions are pinned down with real confidence, because two sun-like stars locked in a tight, well-measured orbit are about the best-studied stars in the sky after our own. Proxima is harder. It is faint, it is small, and red dwarfs age in ways that are notoriously difficult to read. So the question of whether the three stars are true siblings or a later union remains, remarkably, not fully settled, a small unsolved mystery sitting at the heart of the nearest system to our own. And notice what that uncertainty does to the word family, which we have been using so casually. If Proxima was captured, then the thing we call a single triple system is, in a sense, two histories stitched together, a pair of stars that grew up as one, and a lonely third that wandered in from somewhere else and was caught. Even the togetherness of the system might be partly an accident of timing, a gravitational meeting rather than a shared origin. The bond is real either way. The radial velocity measurements settled that. But whether it is a bond of birth or a bond of capture is a different question, and it is one that points at something we will see again and again. The more closely you look at this system, the less it behaves like one unified place, and the more it resolves into separate parts that happen, for now, to be travelling together. There is at least one suggestive clue that the three really do belong together, and it is worth stating fairly, because the honest answer is that the evidence leans toward a shared origin without absolutely clinching it. The three stars move through space along closely matching paths, drifting in the same direction at nearly the same speed, exactly what you would expect of objects born from one cloud and never since parted. That common motion is the strongest reason most astronomers treat them as genuine siblings rather than a chance capture. But leans toward is not proves, and the careful position is to hold the question open. The bright pair were certainly born together. Whether the faint outsider shares that birth or merely joined the procession later is a thread still being pulled, and the whole arrangement is not even sitting still relative to us. We tend to imagine the stars as a fixed backdrop, painted permanently onto the night, but every star is in motion, and this system is drifting through the galaxy on its own path, a path that, at this moment in cosmic history, happens to be carrying it gently toward us. Alpha Centauri is not merely the nearest system, it is in the slow process of getting nearer still. Across the coming tens of thousands of years it will continue to close the gap, until in roughly 28,000 years from now, it will reach its minimum distance from the Sun, drawing in to something like 3 light-years before the geometry turns and it begins, ever so slowly, to pull away again. We happen to be alive during the long approach. Our distant descendants, if any remain, will see these stars slightly brighter in the sky than we do, the nearest system creeping a little closer for hundreds of generations, and then receding for hundreds of thousands more. Even the title of nearest neighbour is not fixed. It is a temporary arrangement in a galaxy where nothing holds its position, and we have simply been born into the window when this particular system is on its way in, rather than on its way out. And notice what this does to the word nearest. We call this the closest star to the Sun, and that title belongs to Proxima, the faint red dwarf is, at this moment, the single nearest star to our own, sitting just over 4 light-years away. But the thing that earns the title is the dim, distant, lonely ember, not the bright pair that actually carries the famous name. The brilliant sun-like stars that we point to in the southern sky, the ones we photograph and write about, are slightly farther from us than the feeble red dwarf is. The most famous part of the system is not even the closest part of the system. The compression of the single name has quietly swapped them in our imagination. Now step back and look at the full hierarchy we have assembled, because this is the architecture the name hides. At the centre, 2 sun-like stars, one yellow and brighter, one orange and dimmer, bound in an 80-year ellipse that breathes between Saturn-distance and Pluto-distance. Far, far outside them, separated by a gulf 400 times wider than their own widest separation, a single faint red dwarf creeps along a 500,000-year orbit, bound to the pair by a gravitational thread so long that light needs months to span it. 3 stars, 3 wildly different objects, and vast, echoing emptiness between the inner pair and the outer ember. This is the heart of why the name deceives. When you hear a single label, your brain builds a single image. One place, one bright dot, one tidy destination. The reality is a structure with dramatically different regions separated by enormous distances, more like a few far-flung islands than a single landmass. To go from the bright stars to the faint one is not a short hop across a crowded system. It is a journey across a gulf comparable in scale to the outer reaches of an entire solar system. And the 3 stars are not merely far apart. They are profoundly different kinds of objects, which means they create profoundly different surroundings. The yellow star, A, is the closest true twin to our own sun that exists anywhere in our stellar neighbourhood comparable in mass, in colour, in temperature, in the quality of its light. A world bathed in its glow would receive warmth and colour not so unlike what Earth receives. The orange star, B, is meaningfully cooler and dimmer, casting a more muted amber light. A world warmed by B would sit in a different kind of glow under a smaller, softer sun. And Proxima, the red dwarf, is a different beast altogether, a tiny, cool star that emits most of its meagre energy in red and infrared light. A star so dim that a planet would have to huddle extremely close just to stay warm. That last point matters enormously, and it sets up everything still to come. Because Proxima is so faint, any world that could hold liquid water would need to orbit it on a very tight leash, far closer than Mercury hugs our sun. And red dwarfs like Proxima are not gentle, they are flare stars, prone to sudden, violent eruptions of radiation that can lash any nearby planet with bursts far more powerful than anything our steady sun throws at the Earth. So the environment around the faint outer ember is radically unlike the environment around the 2 sun-like stars at the centre. One name, but 3 separate worlds of possibility, each with its own light, its own warmth, its own dangers. There is another difference between these 3 stars, and it is one we almost never think to ask about: their ages, and how far each has travelled along its own life. We tend to picture stars as fixed and eternal, but every star is burning through a finite supply of fuel, and where a star sits in that long burn shapes everything around it. The 2 bright suns, A and B, are not young. Careful study of their oscillations and their chemistry places them at somewhere around 5 to 6 billion years old, modestly older than our own sun, which is closer to 4.5 billion. They are not infants and not ancient. They are mature stars, a little further into middle age than the sun is. And the yellow star, being slightly heavier than the sun, burns a little harder and a little hotter for its mass, which means it has already begun the slow brightening that all sun-like stars undergo as they age. A is, in a sense, a glimpse of what our own sun will look like 1 billion or 2 years from now. The same kind of star, just a step further down the road. Their composition matters too, and here is a detail that will become important later in this story. The two bright stars are what astronomers call metal-rich. They contain a noticeably higher proportion of heavy elements, the carbon and iron and silicon and oxygen that make up rock and metal, and ultimately planets, than our own sun does. That is not a trivial footnote. The raw material from which worlds are built was present in abundance in the cloud that formed these stars. Whatever else can be said about the difficulty of making planets here, it is not for lack of ingredients. The pantry was well stocked. Now turn to Proxima, and the contrast in lifespan becomes almost absurd. The red dwarf is a tiny, dense object. Its whole body is only about 1.5 times the diameter of the planet Jupiter, a star barely larger than a giant planet, packed to roughly 30 times the density of our Sun. And precisely because it is so small and so frugal with its fuel, burning at the slowest possible simmer, Proxima will outlast both of its bright companions almost beyond comprehension. The two sun-like stars will age, swell, and exhaust themselves over the coming billions of years, the way our own sun will. Proxima will still be glowing long after they are gone, not for billions of years more, but for trillions. It is the faintest member of the family and also, by an enormous margin, the most enduring. The dim ember is the one that will still be burning when nearly every bright star in the galaxy has died. The least impressive of the three is, in the long accounting of time, the most permanent. Even the night skies within this system would refuse to match our intuition. Stand on an imagined planet circling the yellow star A, and the orange companion B would not be a gentle second sun. Depending on where the 80-year orbit had carried it, B would blaze in the sky as an overwhelmingly brilliant star, sometimes as close, in relative terms, as a distant planet, sometimes drawn back to a more remote point of fire but never the matched, equal twin sun of science fiction posters. And from a world circling distant Proxima, the two bright stars A and B would not even resolve into a pair without strain. They would hang together in the dark as a single dazzling point, a brilliant double star far outshining everything else in that planet's night, yet still unmistakably a star and not a sun. The three stars almost never share a sky as equals. The geometry simply forbids it. This is the picture we have to carry forward, and it is already a long way from the cozy second solar system most people imagine. Not three suns crowded together overhead, not a tight little knot of stars trading places. Instead, a close, restless, 80-year binary of two unequal suns at the centre, and a faint, flickering, flare-prone red dwarf marooned 13,000 astronomical units away on a 500,000-year orbit, bound by the thinnest of gravitational threads. The famous name flattens all of that into a single dot. The reality is an enormous, structured, deeply uneven territory. But naming the pieces is only the first step. We now know the system is made of two sun-like stars locked in a wide breathing ellipse, and one distant ember chained far outside them. The far harder question, the one that turns this from a curiosity into something genuinely strange, is what an arrangement like this does to any world unlucky, or lucky enough to form inside it. Because a planet does not simply ignore a second star. It does not politely orbit one sun while the other looks on. Gravity does not work that way. When you place worlds into a system where the stars themselves are swinging between Saturn-distance and Pluto-distance every 80 years, the orbits those worlds are allowed to keep, the regions where they can survive at all, and the very stability of their existence change in ways that have no parallel in our own tidy solar system. Some regions become safe harbours, others become gravitational no-man's lands where no planet can endure. And the difference between the two decides everything about where worlds can exist here, which is exactly where we are headed next. A planet does not get to choose its sky. It inherits whatever gravity allows, and gravity in this system is not a single steady hand. It is a contest. To understand why Alpha Centauri is so unlike our own orderly home, you have to stop thinking about the stars as scenery and start thinking about them as forces, two of them at the centre, pulling in different directions, never quite agreeing on where anything should go. In our solar system, the Sun is an undisputed monarch. Every planet answers to one ruler, and the arrangement is calm because there is no rival. Here, at the bright heart of the system, there are two rulers, and any world caught between them lives or dies by how it navigates their competing claims. Start with the simplest truth about orbits in a place like this. There are really only two kinds of stable home a planet can hold when two stars share the center, and everything between those two kinds is forbidden. The first kind of home hugs one star tightly, a planet circling close around the yellow star alone, or close around the orange star alone, staying so near its chosen sun that the other star, however brilliant, remains a distant influence rather than a captor. The second kind of home sits enormously far out, beyond both stars together, so remote that the pair blurs into a single source of pull, and the planet simply circles the whole combination as if it were one fat, lumpy mass. Those two zones tight in around one star, or vast out around both, are the only places a world can survive. The wide middle ground between them is a graveyard. Picture why. Imagine a planet trying to orbit the yellow star at a comfortable middle distance, the kind of orbit Jupiter holds around our Sun. For most of the 80-year cycle that might feel survivable. But this binary does not keep a polite, fixed gap. Remember the breathing ellipse from before the two stars swing inward toward each other and then back out. And at their closest approach, the orange companion comes barreling in to a separation far smaller than its average distance. Every time that happens, every close pass, the companion's gravity reaches in and yanks hard on any planet orbiting too far from its host. It is not a gentle, constant tide. It is a periodic, violent tug, delivered again and again across millions of years, each pass nudging the planet's orbit a little more out of true. A world in that middle zone does not settle. It wobbles, then lurches, then finally gets flung, either hurled out of the system entirely into the cold between the stars, or thrown inward to a fiery end. The middle ground is not merely uncomfortable, it is structurally impossible to inhabit for long. This is the single most important thing the eccentric orbit does, and it is worth dwelling on, because it is where the system's geometry turns cruel. If the two stars circled each other in a tidy circle, holding a steady separation, the safe zone around each star would be relatively generous. Planets could orbit fairly far out before the other star's pull became a threat, but this binary does not move in a circle. Its eccentricity of roughly 0.52 means the danger is set not by the average distance between the stars, but by their closest, most aggressive approach. The safe region around each star is shrunk down to fit inside the worst moment of the cycle, not the typical one. The eccentric dance, in effect, reaches inward and prunes back the territory where worlds can live, trimming it far tighter than the comfortable average separation would suggest. The star's restlessness costs every potential planet a great deal of room. So how much room is actually left? When astronomers run the simulations, placing imaginary planets at different distances around each star and letting the gravity of the whole system grind on them for millions of simulated years, a fairly consistent answer emerges. A planet can hold a stable orbit around the yellow star or around the orange star only if it stays within roughly 3 astronomical units of its host. Closer than that, worlds endure. Farther than that, they are progressively destabilized until they are lost. 3 astronomical units is not nothing in our own system that would reach from the Sun out past the asteroid belt toward the realm of the giant planets. But it is a hard ceiling, an invisible wall beyond which the second star's interference becomes fatal. Each of these 2 suns, for all their brilliance, can only protect a modest island of orbital space around itself. Beyond the shoreline of that island, the water churns. But before we even ask whether a finished planet could survive in those islands, there is a deeper and harder question hiding underneath, one that the survival story quietly skips past. Surviving assumes the planet already exists. It assumes a fully formed world is sitting there, and we are only asking whether gravity will let it stay. Yet planets are not placed into systems ready-made. They have to be built, slowly, out of dust and rubble, over millions of years, and the very same restless binary that makes survival difficult makes the building of a planet harder still. The first question is not can a world endure here? The first question is whether a world could ever assemble here at all. Consider how planets form in an ordinary single-star system like our own. a young star is wrapped in a flat disk of gas and dust. Tiny grains drift together, gently bump and stick. Pebbles become boulders. Boulders become mountains. Mountains become the kilometre-sized bodies astronomers call planetesimals, and those in turn collide and merge into worlds. The entire process depends on a delicate condition. When two of these building blocks meet, they must meet slowly. A gentle, low-speed touch lets them clump and grow. The whole architecture of planet building rests on collisions soft enough to stick rather than smash. Now drop a second star into that picture, a heavy companion swinging through an eccentric 80-year orbit, reaching in at every close pass. The companion's gravity stirs the disk of building material like a spoon dragged through it. It does two destructive things at once. First, it truncates the disk, slicing off its outer regions and leaving each star only a shrunken reservoir of raw material to work with. And second, far worse, it whips up the speeds at which the planetesimals cross each other's paths. Instead of drifting and gently kissing, the building blocks are flung onto crisscrossing, mismatched orbits that carry them into one another at violent velocities. And when kilometre-sized bodies of rock collide fast enough, they do not merge. They shatter. The very collisions that are supposed to grow a planet instead grind it back down into fragments. Picture trying to build something larger by hurling two stones together at the speed of a rifle bullet. They do not weld into a bigger stone. They explode into gravel. That is the threat the companion poses to planet building in the bright heart of this system. It does not just endanger finished worlds, it can sabotage them before they are ever born. This is a genuine and unresolved scientific debate, and it is worth being honest about exactly where the science stands, because it is a case of dueling computer models rather than settled fact. Some simulations of planet formation around the bright stars come out pessimistic. When researchers model the stirring of the companion in detail, they find that across much of the warm zone, the collision speeds climb above the shattering threshold, and the growth of rocky planets stalls. The building blocks break each other apart faster than they can accumulate. By that, the habitable zones of A and B might be regions where worlds simply could not finish forming. Other simulations are more optimistic. They point out that the disk of gas, while it lasts, can act as a kind of cushion, and a shepherd gentle drag from the gas can herd the planetesimals onto more orderly, aligned orbits, lowering the speeds at which they meet and quietly reopening the door to growth. By that, if the timing is right and the disk behaves, rocky worlds could still assemble, just more precariously than they did around our lonely sun. Notice the careful labeling here, because it matters. We are not looking at an observed fact about how planets formed in this system. We are looking at competing modelling results, rival simulations, built on different assumptions about the disk, reaching different conclusions. The pessimistic models and the optimistic models cannot both be the whole truth, and the only way to settle the argument is not to compute harder but to look harder, to actually find out whether rocky worlds are there or not. This is precisely why the planet hunting that we are about to turn to carries such weight. It is not merely a search for new dots of light. It is a test of whether the bright stars manage to build anything at all in the one region we most care about. A referee, finally, for a debate that the equations alone cannot end, and it deepens the central strangeness of this place. We already saw that the bright stars create a constrained, competitive environment for keeping planets. Now we can see that they may impose a second tax, levied earlier, on making them in the first place. Two obstacles stacked one atop the other. The difficulty of building a world here, and then the difficulty of holding on to it. The faint red ember, by contrast, sidesteps the first obstacle just as it sidesteps the second. With no close companions stirring its disk, Proxima could assemble its small, tight family of worlds in relative peace, free of the shattering collisions that may have haunted the bright pair. Once again, the system inverts our expectations. The welcoming-looking suns face the steeper climb, both in birth and in survival, while the dim outsider quietly gets on with the business of having planets. And here is the part that turns a constraint into a genuine possibility, the detail that keeps this story from ending in disappointment. The region where a planet would need to sit to be comfortably warm, the so-called habitable zone, where a world receives enough light to keep water liquid, but not so much that it boils away, falls comfortably inside that 3 astronomical unit safe island. For both stars, for the yellow star, brighter than our Sun, the warm zone sits a little farther out than Earth's distance, somewhere around 1¼ astronomical units. For the cooler orange star, the warm zone huddles closer in, roughly half to 9/10 of the Earth-Sun distance, because a dimmer star must be approached more closely to feel the same warmth. Both of those comfortable bands lie well within the stable territory. In other words, the geometry is tight, but it is not hopeless. There is room just barely, just enough for a temperate world to circle either Sun-like star on an orbit that gravity will permit to survive for billions of years. The safe harbour and the warm harbour overlap. That overlap is the entire reason anyone bothers to look here at all. Now consider the other kind of stable home, the vast out option, because it explains why one particular fantasy can be quietly retired. There is a romantic image people carry of a world circling both suns at once standing on its surface. You would watch 2 stars rise together and set together, 2 warm companions sharing the same sky. To hold that kind of orbit, circling the pair as a unit, a planet cannot sit at a friendly middle distance, because the middle is the graveyard we already described. It would have to retreat enormously far out, well beyond the stars, far past the cold edge where any warmth has faded, out to distances of many tens of astronomical units before the 2 stars' competing pulls would finally smooth into a single, stable, combined tug. You would have to step so far back that the 2 suns merged into one blurred point of light, the way 2 close lamps seen from across a darkened valley fuse into a single glow. And at that distance, the light arriving would be feeble, the warmth negligible, the surface frozen. So yes, a world circling both suns together is dynamically allowed, but only out in the deep cold, never in the temperate middle. The cosy double sunset world, bathed in the light of 2 nearby stars at once, is exactly the configuration gravity forbids. The comfortable distances are unstable, and the stable distances are uncomfortable. The 2 requirements refuse to meet. This is the deep strangeness of the bright heart of Alpha Centauri, and it has no parallel in our experience. Our solar system is one warm island with a single ruler and acres of stable room. The Alpha Centauri pair offers 2 small warm islands, each clinging tightly to its own star, separated by a churning gravitational sea that nothing can cross and inhabit. A planet here must commit. It must belong to the yellow star or to the orange star, living deep inside one star's protective grip, treating the other forever as a distant, brilliant outsider. It cannot split the difference. There is no neutral ground, no shared territory, no diplomatic middle. The architecture demands allegiance to one sun and punishes any world that tries to serve both. And what would the sky look like for a world that had made its choice? Suppose a planet circles the yellow star in its warm zone, the most sun-like situation available anywhere in our stellar neighbourhood. By day, its sky would be lit by a star almost indistinguishable from our own similar colour. Similar warmth, casting light, a human eye would find utterly familiar. The seasons, the climate, the very quality of daylight would be governed by that one star, because the orange companion, for all its fierceness, sits far too distant to deliver meaningful heat. But at night, and in the gaps of the day, that companion would announce itself spectacularly. The orange star would blaze in the planet's sky as an overwhelmingly bright point, not a disk, not a second sun warming the ground, but a single dazzling spark hundreds of times brighter than any planet or star we ever see in our own night, brilliant enough to cast faint shadows, far too bright to look at comfortably. And because the 2 stars swing through their 80-year ellipse, that spark would slowly change over a lifetime, drawing closer and growing more intense across decades, then easing back toward a more remote, dimmer point, a presence in the sky that breathes on a scale longer than any single human memory. The warmth comes from one sun, the drama comes from the other. They never blend into the gentle twin suns of imagination. One rules the day, the other haunts it. For a world circling the orange star instead, the picture would invert in tone. The home sun would be cooler and dimmer, its light shifted toward amber, its warm zone hugging closer in. The daylight would be softer, more muted, the sun in the sky a little smaller and less fierce than our own, and the yellow star, the brighter of the two, would take the role of the brilliant nighttime intruder. An even more dazzling spark than the orange star appears from the other side, because it is the more luminous of the pair. Each of these two possible worlds would experience the other's star as a magnificent, variable beacon, never as a companion sun. The geometry guarantees it. The stars are bound together, but they hold their planets apart, each world locked to its own master, gazing across the gravitational sea at a brightness it can never approach. Now lift your eyes from the bright pair entirely and travel back out to the faint red ember, because Proxima changes the entire conversation, and in the most unexpected way. After everything we have just said about competing forces and forbidden middles and pruned-back safe zones, you might assume the third star's situation is the most chaotic of all. It is the opposite. Proxima Centauri, marooned 13,000 astronomical units from the bright pair, is so absurdly far from the gravitational contest at the centre that, for any planet circling it, the two sun-like stars effectively vanish as a dynamical force. The pull of A and B on Proxima's worlds across that immense gulf is so diluted as to be nearly irrelevant to the day-to-day business of holding an orbit. A planet around Proxima does not have to navigate two rulers. It answers to one its own small red star, and that is all. This is the great irony of the system's structure. The two bright, sun-like stars at the centre, the ones that look most welcoming, create the most gravitationally hostile and constrained environment for planets, a place of pruned islands and forbidden seas. The faint, lonely, dim red dwarf far out in the dark, the least impressive star of the three, offers the calmest and simplest planetary setup of all. A clean, ordinary single-star system, dynamically speaking, where worlds can circle without being torn between masters. From the surface of a planet orbiting Proxima, the two bright stars would not be looming suns or dangerous neighbours. They would be a single brilliant point of light in the night sky, a dazzling double star, the most striking object in that planet's heavens, far outshining anything else there, yet contributing essentially no warmth and no gravitational meddling. They would be a beautiful ornament, nothing more. The drama of the binary, so dominant at the centre, fades to mere decoration by the time you reach Proxima's distant realm. But, and this is where the system refuses to give anyone an easy victory, dynamical calm is not the same as safety. Proxima may spare its planets the gravitational tug-of-war, but it replaces that danger with a different one, just as severe and entirely its own. Proxima is a red dwarf, and red dwarfs are stingy with light. To stay warm enough for liquid water, a planet must orbit Proxima on an extraordinarily tight leash, far closer to its star than even Mercury hugs our Sun, circling in a matter of days rather than months or years, and huddling that close to a red dwarf carries a price. These small stars are violently temperamental. They are flare stars, given to abrupt, savage outbursts that can flood their nearby planets with radiation and high-energy particles on a scale our own placid Sun never approaches. A world warming itself at Proxima's feeble fire sits directly in the blast radius of that fire's tantrums. So, the trade is laid bare. The bright stars offer sun-like light, but a brutally constrained, competitive gravitational environment. The faint star offers gravitational peace, but a harsh, flare-scarred, radiation-soaked existence pressed up against an unstable little furnace. Neither setting is a simple second Earth. Each is its own bargain, its own particular set of dangers. There is also the matter of how a planet so close to a red dwarf would turn or fail to turn. A world orbiting that near to its star is almost certainly gripped by tidal forces strong enough to lock its rotation, so that the same face is held perpetually toward the star, while the other side is held perpetually toward the dark. One hemisphere in eternal day, one in eternal night, with the star nailed motionless in the sky, never rising, never setting. That is a profoundly alien way for a world to exist, nothing like the spinning day and night rhythm we take for granted, and it flows directly from the geometry red dwarf warmth demands. The dynamical simplicity of Proxima's system buys a planet calm orbits, but the closeness that calm requires reshapes the very experience of standing on such a world. into something we have no earthly reference for. It is worth following that tidal lock all the way to its consequences, because it does something to a planet's climate that has no counterpart anywhere in our own system, and it decides whether such a world is a frozen and scorched ruin or something a great deal more interesting. Begin with the basic geography that a locked rotation imposes. One entire hemisphere faces the star forever, a permanent day that never ends. The star fixed at the same spot in the sky, neither rising nor setting, simply hanging there, hour after hour, century after century. The opposite hemisphere faces away forever, a permanent night of equal and unbroken length. A half of the world the star's light has never once touched. And between those two extremes, encircling the planet like a seam, runs a band where the star sits permanently on the horizon. A ring of eternal twilight, a perpetual dawn that is also a perpetual dusk, neither fully lit nor fully dark. Left to themselves, those two hemispheres would drift toward catastrophe. The day side, under a star that never moves, would bake relentlessly, its heat piling up with nowhere to go. The night side, never warmed at all, would plunge toward a cold so deep that it poses the gravest threat of all to such a world. The air itself could freeze. On a planet with a thin or fragile atmosphere, the gases that make up that atmosphere could migrate to the frozen far side and simply freeze out onto the surface, collapsing into drifts of frozen air, stripping the whole world of the blanket it needs. A tidally locked planet, left without help, tends to tear its own climate in two, an oven on one face, a frozen graveyard of fallen atmosphere on the other, and the star itself makes that fragile atmosphere harder to keep. Proxima is not a quiet sun. It is among the more ferociously active flare stars known, a small body that erupts again and again without warning, capable of sudden superflares that, in a matter of seconds, can send its brightness soaring to many times its ordinary level before falling back to its usual faint state. Picture a furnace that does not merely glow but periodically detonates, hurling out radiation and charged particles in sudden, savage pulses. Now place a planet in permanent daylight in front of it, and notice the cruelty of the geometry we just built. A spinning world gets a reprieve its surface turns, carrying each patch of ground out of the firing line and into the shelter of night, so no single region absorbs more than its share. A tidally locked world gets no such mercy. The same hemisphere is held toward the star forever, which means the same hemisphere catches blast after blast after blast, never once rotating away, soaking up every eruption across billions of years. The relentlessness is the real menace here, more than the violence of any single flare. Not one catastrophic strike that a world might recover from, but an unending bombardment falling forever on the same unlucky face, stripping the air a little thinner with each outburst, and searing the lit ground beneath. The very stillness that defines a tidally locked planet, the fixed star, the unmoving day becomes, under a flare star, a sentence of perpetual exposure. But there is a rescuer, and its name is the atmosphere itself, provided the planet has managed to keep one. A sufficiently thick envelope of air, or a deep enough ocean, does something the bare rock cannot. It moves heat. Winds blowing off the scorched day side carry warmth around the planet toward the frozen night side. Currents and circulation spread the star's energy across the whole globe, rather than letting it pool in one hemisphere. A world with a robust atmosphere can take the searing, concentrated heat of its permanent day and redistribute it, gentling the extremes, keeping the night side warm enough that the air never freezes out, smoothing the brutal divide into something survivable. The atmosphere is the circulatory system that keeps a locked world from killing itself. With one, the planet can be a single connected climate. Without one, it is two dead hemispheres and a thread of twilight between them. And that thread of twilight is where this becomes genuinely tantalizing. On a tidally locked world, the ring of perpetual dawn might be the one place where conditions stay temperate year-round. Never the blistering glare of the high day side, never the lethal dark of the deep night side, but a permanent soft illumination, the star forever low on the horizon. Some models of these worlds suggest that even when the day side is too hot and the night side too cold, that twilight band could remain habitable, a circular ribbon of mild climate wrapping the entire planet. A world where life, if it existed at all, might be confined to a single great loop of perpetual dawn not scattered across continents under a travelling sun, but strung along the one line where the star neither climbs nor sets. It is a profoundly unearthly arrangement, and it flows directly and inescapably from the geometry that red dwarf warmth demands. Hold this against the bargain we have been tracing all along, because it completes it. The faint red ember offers a planet gravitational peace, no second star tearing at its orbit, a calm and simple single-star home. But the closeness that this dim star forces upon any temperate world extracts its price in a different currency. Not orbital chaos, but a locked rotation that splits the planet into permanent day and permanent night, and a climate that lives or dies entirely on whether an atmosphere survives to carry heat across the divide. The flares we spoke of earlier threaten precisely that atmosphere, and now we can see how much rides on it. The air is not merely a comfort on a Proxima world, it is the one thing standing between a temperate, connected planet and a world torn into a baked hemisphere, a frozen hemisphere, and a single lonely ring of dawn. Whether any planet around the red dwarf has held on to that saving atmosphere is, of course, not something gravity or geometry can answer. It is something that only observation can decide, and observation is exactly where we are about to go. Step back now and hold the whole gravitational portrait in view, because it has rearranged the system into 3 distinct domains, each governed by different rules. At the centre, around the yellow star, a tight warm island where a sun-like world could in principle exist, hemmed in by the 3 astronomical unit wall and watched over by a brilliant orange intruder. Beside it, around the orange star, a second tight warm island under softer amber light, with the yellow star playing the dazzling outsider. Between and beyond those 2 islands, a forbidden gravitational sea where no temperate world can survive. And far, far out in the dark, around the red ember, a dynamically calm but environmentally savage realm, where worlds may orbit in peace but must endure flares and eternal tidal stillness to do it. One name, 3 domains, 3 completely different sets of rules for where a planet may live and what its life would be like. Notice how thoroughly this dismantles the comfortable picture we started with. The phrase nearest star system conjures a single tidy place, a near copy of home. What gravity actually carves out is a divided territory of incompatible zones, some sunlit but cramped, some peaceful but punishing, separated by gulfs and by forces that forbid any world from belonging to more than one domain at a time. To ask whether Alpha Centauri has habitable planets is not one question. It is at least 3 separate questions, each with a different answer. Because each star builds a different world, the system does not offer a second solar system. It offers 3 competing experiments in how to survive among stars, run side by side under a single misleading label. And that raises the question that has been waiting beneath all of this. We have spent these minutes establishing where worlds could exist, the tight islands around the bright stars, the calm but harsh realm around the red dwarf, the forbidden sea between. But could and does are not the same word. The gravitational map tells us which homes are permitted. It does not tell us which homes are actually occupied. For decades, that distinction was the whole agony of studying this system. We could calculate beautifully where a planet ought to be able to live, and we could not, for the longest time, prove that any planet was truly there. The map of possibility was clear. The map of reality was almost blank. That gap has finally begun to close unevenly, dramatically, and not at all the way most people assume. Around one of these 3 stars, worlds have now been confirmed beyond doubt, pinned down, measured, even argued over and corrected. Around another, a single tantalizing shadow of a planet flickers in and out of view, glimpsed once and then lost, hovering in that uncertain space between discovery and mirage. And the famous old claim that a world had been found, the one that launched 1,000 headlines, has not entirely survived the harder look that newer instruments have given it. The truth of what actually orbits these 3 stars is messier, more recent, and more honest than the confident stories we tend to tell, a precise ledger of what is proven, what is disputed, and what remains only a haunting maybe. That ledger is where we turn next. Now we move from could to does, and the moment you make that move, you have to become disciplined about a distinction that most space stories blur on purpose. There is a difference between a confirmed planet, a candidate, a disputed signal, and a result that has been actively overturned. These are not shades of the same thing. They are entirely different categories of knowing. A confirmed planet has survived independent checks by separate instruments and separate teams. A candidate is a real, intriguing hint that has not yet cleared that bar. A disputed signal is one that some experts accept and others reject. And an overturned result is a claim that was once made and has since been knocked down by better data. As we walk through what actually orbits these three stars, I'm going to keep those labels sharp, because the honest version of this story is far stranger and far more interesting than the tidy headline version, and the difference between the labels is exactly where the real science lies. Begin where the ground is firmest, which means leaving the two bright sun-like stars behind for now and travelling all the way back out to the faint red ember, Proxima Centauri. This is the surprise that catches almost everyone off guard. The dim, distant, flare-prone little star, the least impressive of the three, the one marooned 13,000 astronomical units out in the dark, is the only member of the entire system around which we have genuinely confirmed planets. Not the brilliant yellow sun, not its orange companion, the lonely red dwarf, the two grand sun-like stars at the centre, for all their welcoming light, have yet to yield a single confirmed world. The proven planets all belong to the ember. The first of them, and the most famous, is Proxima Centauri B. It was announced in the year 2016 by astronomers at the European Southern Observatory, after years of painstaking work watching the star for the tiny rhythmic wobble that an orbiting planet imprints on its host. That technique measuring the faint to and fro tug a planet exerts on its star is called the radial velocity method, and for Proxima B it delivered a clean, repeatable, confirmed signal. This is a real world. It carries at least about 1.1 times the mass of the Earth, making it a genuinely Earth-mass planet rather than some bloated giant. And critically, it orbits squarely within Proxima's habitable zone, the band where a planet receives just enough warmth for liquid water to be possible on its surface. The nearest confirmed planet to our own solar system is, by mass, a cousin of the Earth, sitting in the one region around its star where water could in principle stay liquid. But hold that excitement against everything we established about red dwarfs, because Proxima B is a perfect lesson in why habitable zone does not mean habitable. To sit in Proxima's warm band, the planet must huddle astonishingly close to its feeble star circling at roughly 5/100ths of the Earth-Sun distance, around 20 times closer to Proxima than we are to the Sun, completing a full orbit in just over 11 days. A year on Proxima B lasts less than a fortnight, and pressed that close to a flare star, the planet is exposed to exactly the violence we described, bouts of intense radiation that could, over time, strip away an atmosphere entirely or chemically batter whatever atmosphere survives. Whether Proxima B actually holds onto air, and whether anything could endure beneath it, remains genuinely unknown. We have confirmed the planet. We have not confirmed that it is hospitable. Those are separate facts, and the gap between them is enormous. What we can say with confidence is the narrow, honest thing. An Earth-mass world exists, in the warm zone, around the nearest star, and everything beyond that is still an open question. The second confirmed world around Proxima is newer, smaller, and in its own way even more impressive as a feat of measurement. It is called Proxima Centauri D. Its story is a clean illustration of how the candidate to confirmed pipeline is supposed to work. The first faint hint of it appeared as a weak signal buried in radial velocity data gathered around the year 2020, while astronomers were actually trying to pin down the mass of Proxima B. A suspicious little rhythm with a period of about 5 days kept surfacing in the numbers. In early 2022, a team formally proposed it as a candidate, explicitly a candidate, not a confirmed planet, because a single hint in one dataset is not proof. And then the system worked exactly as it should. Using a powerful new instrument, purpose-built for hunting planets around small cool stars, a near-infrared planet searcher brought online in Chile, astronomers independently confirmed Proxima D in work published in the year 2025. A separate instrument, a separate analysis, the same planet. That is what confirmation looks like. and what a strange little world it turned out to be. Proxima D is a sub-Earth smaller than our own planet, carrying only about a quarter of the Earth's mass, which makes it roughly twice the mass of Mars. It is one of the lightest planets ever detected by the wobble method anywhere. It orbits even closer to Proxima than planet B does, whipping around the star in only about 5 days, far too close and far too hot to sit in the habitable zone. Its surface would be punishingly warm. But its importance is not about habitability. Its importance is that it proves the nearest star hosts not just one world but a whole compact little planetary family. Multiple confirmed worlds threaded tightly around a single dim ember. The closest planetary system to our own is not a lonely single planet. It is a miniature system in its own right, and we have now confirmed at least 2 of its members. So that is the firm ground. 2 confirmed planets around Proxima, B and D. Both real, both checked, both genuinely there. Now we step deliberately onto shakier footing, because the 3rd supposed planet of Proxima is a cautionary tale, and exactly the kind of thing the labels exist to handle honestly. Its name is Proxima Centauri C, and for a few years it lived in the hopeful space of a candidate. The first hints of it emerged around the year 2020, suggesting a much larger, much more distant world circling Proxima on a long orbit of roughly 5 to 6 years far out in the cold. There was even a tentative whisper of a possible direct image, a faint point of light that might, just might, have been the planet itself. It was an exciting prospect. A 3rd world, a heavier one, out in the frigid reaches of the red dwarf's domain. But excitement is not evidence, and Proxima C did not survive the harder look. Even early on, some astronomers disputed the signal, arguing that the wobble attributed to a planet might instead be an artifact of the star's own restless activity, the magnetic churning and spotting of a red dwarf can mimic, in the data, the gentle tug of a planet that is not really there. The signal was disputed, rather than settled. And then came the decisive test, when that same powerful new near-infrared instrument that confirmed Proxima D turned its precision on the system in the year 2025, it did not just fail to strengthen the case for Proxima C, it actively worked against it. The new observations were unable to confirm the planet, and the careful analysis pointed toward Proxima C being, most likely, not a real world at all. The most famous follow-up claim in the system had been, in effect, refuted by better data. Sit with what just happened, because it is the whole point of this story. Around a single star, in the space of a few years, the same generation of instruments confirmed 2 genuine planets and demolished a 3rd that people had once celebrated. That is not a failure of science. That is science functioning exactly as it should, proposing, testing, and discarding what cannot withstand scrutiny. If we had told you flatly that Proxima has 3 planets, we would have been repeating a claim that the evidence no longer supports. The honest ledger reads, 2 confirmed, 1 effectively overturned. And the discipline that produced that ledger is precisely what should make you trust the 2 that remain. And the orange star, B, has its own cautionary tale, older, more famous, and more completely demolished than even the story of Proxima C. It deserves a full hearing, because for a while, it was the most celebrated planet claim in the entire neighbourhood of the Sun, and its collapse is the single best lesson this whole system has to teach about the gap between a signal and a world. Rewind to October of the year 2012. A European team, working with the same precision wobble hunting instrument at La Silla in Chile that would later prove so productive, announced in the journal Nature that they had found a planet around the orange star. They called it Alpha Centauri Bb. It was, they reported, a world of roughly Earth's mass, whipping around the orange star in just 3.2 days, on an orbit so tight it sat at about 1/10 of Mercury's distance from its sun, a scorched ball of rock with a surface that would run with molten lava. It was not a place for life. But that hardly mattered to the excitement, because of what it represented. The first planet ever detected around a sun-like star in the closest system to our own, an Earth-mass world right next door. The lead author called it a major step toward finding a true twin of the Earth in the immediate vicinity of the Sun. Headlines around the world hailed it as a landmark. The closest exoplanet to humanity had, it seemed, been found. but look closely at how thin the thread was, because this is where the discipline of the labels earns its keep. The wobble the team had to measure was astonishingly small, a back and forth motion of the star of only about half a metre per second, slower than a casual walking pace, and right at the ragged edge of what the instrument could reliably detect. To pull a signal that faint out of the data, the team had to mathematically strip away a whole forest of larger disturbances, the churning of the star's own surface, its spots and its rotation, and the looming gravitational influence of the bright companion, A. The supposed planet was not a bold, clear signal. It was a whisper, extracted from noise by heavy processing, sitting at the very limit of the possible, and almost immediately some astronomers were uneasy. One prominent exoplanet expert, writing a commentary that ran alongside the discovery itself, praised the team's skill, but cautioned that what they had was a weak signal buried inside a larger, more complicated one, exactly the kind of situation where a phantom can masquerade as a planet. The unease was justified. 3 years later, in the year 2015, a team based at Oxford published a reanalysis with a title that says Everything, Ghost in the time series. They went back to the very same data and asked a devastating question. The observations of the orange star had not been taken smoothly and continuously. They had been gathered in irregular bursts, with gaps a night here, a stretch of nights there, long silences in between. The Oxford team showed that this irregular pattern of when the data was collected could, all by itself, manufacture a fake rhythm in the numbers, a periodic signal that looks for all the world like an orbiting planet, but is really just an echo of the observing schedule. To prove it, they did something elegant and merciless. They built synthetic datasets containing no planet at all, pure noise, sampled on the same lumpy timetable as the real observations, and ran the same analysis. And the planet appeared anyway. A 3.2-day signal, statistically convincing, conjured out of data that contained no planet whatsoever. The ghost walked out of the machine on command. That was the end of Alpha Centauri Bb. The signal that had been celebrated as the nearest Earth mass world was, in all likelihood, never a world at all, just an artifact of the gaps between observations, dressed up by the analysis to look like a planet. And here is the detail that shows the system working as it should. The original discoverer accepted it. The lead author of the 2012 announcement publicly conceded that, in his own words, the planet was probably not there. No defensiveness, no clinging to the headline. The claim had been tested, it had failed, and the people who made it acknowledged the failure. That is not science embarrassing itself. That is science correcting itself, the most important thing it knows how to do. So when I said a moment ago that the orange star sits in an empty silence, you can now hear how loaded that silence is. It is not the silence of a star no one has bothered to study. It is the silence left behind after a famous planet was announced there, believed there, and then erased there. The orange star has already taught us, more thoroughly than any other member of the system, that a signal is not a world until it has survived every attempt to kill it. Now, finally, we turn to the two bright sun-like stars at the centre, the ones everyone assumes must be the real prize, the most promising places of all. And here the story becomes its most tantalising and its most frustrating, because around those welcoming yellow and orange suns, after decades of searching, we have not a single confirmed planet. What we have around the yellow star is the most exquisite, maddening candidate in the entire neighbourhood of the Sun, a world that has been glimpsed, glimpsed again, lost again, and reconstructed largely through simulation. It is the perfect embodiment of the word candidate, and its saga is worth telling carefully because it is the freshest and most dramatic turn in this whole account. The hunt around the bright pair is brutally hard, and the reason traces straight back to the architecture we mapped at the very start. The two sun-like stars are luminous, which is wonderful for the prospect of warm planets but terrible for the act of seeing them. A planet is fantastically faint next to its star, and here the problem is doubled. Even if you cleverly mask the glare of the yellow star, the orange companion is sitting close by in the field of view, flooding the same patch of sky with its own light. You are trying to spot a candle beside a searchlight, while a second searchlight blazes just over your shoulder. That overlapping double glare is the central obstacle, and it is why the bright stars, despite being the most sun-like targets imaginable, have resisted planet hunters far more stubbornly than the dim red dwarf ever did. The first real hint around the yellow star came in the year 2019. Astronomers using a major ground-based telescope in Chile, equipped with a newly developed system for imaging in the mid-infrared, caught a faint point of light near the yellow star, a possible directly imaged planet, sitting roughly in the warm zone, at about 1 astronomical unit from its host. It was a thrilling glimpse, but the observing run was short. The signal was at the very edge of what the instrument could trust, and the astronomers were careful and honest about it. They could not say whether the point of light was a planet, or a clump of warm dust, or simply an artifact of the instrument itself. It was logged as a candidate, and intriguing maybe, and it could not be confirmed from the ground. The glare and the limits of Earth-based imaging left it hanging. To push further, you needed to get above the atmosphere, and you needed the most powerful space telescope ever built. In August of the year 2024, astronomers turned the James Webb Space Telescope using its mid-infrared instrument and a coronagraph, a precision mask designed to blot out a star's light toward the yellow star. After enormous effort to subtract the glare of both bright stars, they revealed an object more than 10,000 times fainter than the yellow star, sitting at a separation of about twice the Earth-Sun distance. For a moment, it looked like the breakthrough, a point of light in the right kind of place around the nearest sun-like star. The team was even able to establish that it was not a background galaxy, not a foreground asteroid drifting between the telescope and the star, and unlikely to be a mere instrumental ghost. Something was really there in that August image. And then came the twist that defines this candidate. The team went back for confirmation, taking further observations with the same space telescope in February and again in April of the year 2025. In both of those follow-up looks, the object was gone. It did not reappear. One of the lead astronomers described it, memorably, as the case of a disappearing planet. A single sighting, followed by 2 non-detections, is not how a confirmed discovery is supposed to behave. By the strict rules of the labels, 2 misses after 1 hit ought to be deeply discouraging. But here the story takes its cleverest turn, and it is a beautiful example of how modern astronomers extract meaning from absence. Rather than simply giving up, the team asked a precise question. If a planet really had been there in August, on a plausible orbit around the yellow star, how often would it have been hidden from view in February and April? Remember the gravitational constraints we traced earlier. Any real planet here must follow an orbit that stays stable against the pull of the orange companion. So the astronomers simulated millions of possible stable orbits consistent with the single Webb sighting, and with the earlier 2019 ground-based glimpse, then checked how many of those orbits would have carried the planet too close to the star's glare to be seen during the 2 follow-up attempts. The answer was striking. In a little over half of the simulated stable orbits, the planet would indeed have been lost in the star's light precisely when they looked in early 2025. The disappearance, in other words, was not evidence against the planet. It was exactly what a real planet on many plausible orbits would have done. The non-detections were consistent with the world being real and simply out of sight. From the brightness of that one solid August detection and the family of allowed orbits, a portrait emerged of what this candidate might be. It appears to be a gas giant, roughly the mass of Saturn, looping around the yellow star on an elongated, eccentric path that carries it within the star's habitable zone, moving somewhere between about 1 and 2 times the Earth-Sun distance over the course of an orbit, lasting on the order of 2 to 3 years. If it is real, it would be the closest planet to Earth ever found orbiting in the habitable zone of a sun-like star. And yet this is crucial, and the astronomers themselves stress it being a gas giant. It would not be a home for life as we know it. A Saturn-like ball of gas does not have a surface for oceans or continents. Worse, for anyone dreaming of an Earth twin around the yellow star, a giant planet sitting in the habitable zone would gravitationally dominate that region. Its mass, sweeping the warm band clear of any smaller rocky world that might otherwise have formed there. One researcher put it vividly, saying such a giant would clear the zone much as a bowling ball clears its pins. So even in the best case, this candidate is not the second Earth of the headlines. It is something rarer and stranger, a possible nearby gas giant, sitting where an Earth might have been, and possibly preventing one from existing at all. And I must be exact about its status, because this is the living unfinished frontier of the whole subject. As of now, this world around the yellow star is a candidate, not confirmed. It rests on one strong detection in 2024, one inconclusive earlier glimpse from 2019, two non-detections in 2025, and a great deal of careful orbital modelling that makes the case plausible but not closed. The findings were laid out in papers accepted in a major astrophysical journal, and the scientists involved have been admirably cautious. One outside expert noted dryly that he has seen planet candidates come and go, and that it is simply too early to call this object a planet. The team itself has a clear next step. If the candidate is real and follows its expected orbit, it should swing back into a visible position beside the yellow star around August of the year 2026, and the plan is to point the space telescope at it again then to see whether the disappearing planet reappears on cue. We are, quite literally, waiting on the sky. The confirmation, if it comes, lies just ahead of us. Notice, too, the historical tangle, because it shows how messy real discovery is. The faint candidate glimpsed from the ground in 2019 and the object Webb caught in 2024 were seen at somewhat different separations from the star, the earlier one closer in, the later one farther out. Rather than treat them as two unrelated puzzles, the astronomers considered the most economical explanation, that they are the same single planet, caught at different points along its elongated eccentric orbit, the orbit simply carrying it nearer and farther from the star as the years passed. Folding the old glimpse and the new detection together into one moving world is part of what makes the candidate compelling. But it is also a reminder that we are assembling a planet here out of scattered glimpses across years, like reconstructing an animal from a few footprints found in different seasons. It is real detective work, and the verdict is not yet in. It is worth pausing on something that all of this searching has quietly produced, something that sounds like failure but is actually a form of knowledge. After decades of hunting, with steadily improving instruments, astronomers have not only found planets here, they have also ruled large regions of these systems empty. Around Proxima, the long campaigns of precise measurement have grown sensitive enough to exclude whole categories of undiscovered worlds. The data now shows there is no further planet above a certain modest mass tucked into the short orbits, no hidden heavyweight lurking unseen in the warm zone, no large companion that the searchers would have caught by now. The absence is measured, not assumed. It tells us that Proxima's tight little family of confirmed worlds is most likely close to complete, not the visible fragment of some larger hidden system. This is a subtle but important point about how this kind of science accumulates. A non-detection, done carefully, is not nothing. When an instrument is good enough that it would have seen a planet of a given size had one been there, then not seeing it becomes a real result, a fence drawn around what can still be hiding. Every year the fences tighten. The empty zones become more confidently empty, the confirmed worlds more confidently counted, and the candidates more sharply isolated as the genuine open questions they are. The map of this system is being drawn not only by what we find, but by what we can now prove is not there to be found. All of which raises the obvious question: how will we ever settle the things still hanging in the balance? The candidate gas giant around the yellow star, awaiting its relook. The empty silence around the orange star, where one world has already dissolved. The lingering possibility of a small rocky planet hiding in a warm zone, too faint for anything so far to catch. These are not questions that careful reanalysis of old data can close. They need new eyes, and, remarkably, there is now an instrument being built for almost exactly this purpose. A small telescope designed from the ground up to crack the one system that has resisted everyone. Its name is Tollyman itself, drawn from the old name for the system. The same root as Tollyman, the orange star and the cleverness of it, lies in refusing to play the game that has defeated every previous attempt. Recall the central obstacle around the bright pair, the overwhelming double glare, two brilliant sun-like stars flooding the field, drowning any faint planet in light. Every method we have discussed so far tries, in one way or another, to fight that glare directly to mask it, subtract it, or peer through it to glimpse the planet itself. Ptolemy does not try to see the planet at all. It does something indirect and, in its way, far more cunning. It watches the two bright stars and measures, with almost absurd precision, the exact separation between them, and then waits for that separation to wobble. Here is the logic. If a planet is circling one of those bright stars, its gravity tugs on that star, pulling it a tiny distance back and forth as the planet orbits. That motion is minuscule, far too small to notice by ordinary means, but it slightly rhythmically changes the apparent gap between the two stars. A hidden world betrays itself not by its own light, which is hopeless to capture, but by the faint, telltale rocking it imposes on the position of the star it orbits. Measure the distance between the two bright stars finely enough, for long enough, and a planet that no telescope can see will announce itself in the wobble of the numbers. It is detection by inference, the same fundamental idea as the wobble hunting that found the worlds around the red dwarf, but turned to the geometry of the binary itself, reading the planet's presence in the shifting separation of the pair. The precision required is staggering, and it is worth pausing on just to feel the scale of the challenge. The deflection Ptolemy is hunting for amounts to a few millionths of a single arc second, an angle so small it is like trying to measure the width of a coin lying on the surface of the moon. To pull that off, the telescope uses an unusual trick of optical design. Rather than focusing each star to a tight, ordinary point, it deliberately spreads the starlight into an elaborate, structured pattern, a kind of intricate floral spray of light, and that very pattern, paradoxically, is what makes the fantastically fine measurement possible. By turning each star into a richly detailed shape rather than a featureless dot, the instrument can register shifts in position far smaller than a conventional telescope ever could, and can tell the difference between a real planetary signal and the inevitable quivering of its own optics. It is a small telescope, modest in size, low in cost, built to fit on a compact spacecraft, but it is purpose-built to do the one thing the great observatories, for all their power, struggle to do here, and the target is exactly the gap in our ledger. Ptolemy is aimed squarely at the two bright sun-like stars, the very places where we have a flickering candidate and an empty silence, and not one confirmed world. Its stated goal is the thing that has eluded everyone, to find a rocky, potentially temperate planet in the habitable zone of the yellow star, or the orange one, the kind of world that direct imaging may never catch, and that the heavy double glare has hidden for decades. It is a search engineered against the specific obstacle this specific system throws up. The mission is led from the University of Sydney, backed by the privately funded breakthrough initiatives, and with involvement from NASA's Jet Propulsion Laboratory and other partners, and it is under construction now, with a launch into low orbit around the Earth targeted for roughly the year 2027, followed by years of patient watching. Step back and notice what is happening to our methods across this whole account, because it is a quiet theme worth making explicit. 3 different stars, 3 different kinds of evidence, 3 different ways of knowing. Around the faint red dwarf, the confirmed worlds were caught by the radial velocity wobble, watching a single star rock toward and away from us as its planets tug it along the line of sight. Around the bright yellow star, the haunting candidate was glimpsed by direct imaging, actually capturing the faint photons of the object itself, against all the difficulty of the glare. And now, around the bright pair, the next assault will come by astrometry, measuring the sideways wobble in the very separation of the two stars. Each method is suited to a different situation, and each has its own failure modes, its own ghosts. It is no accident that the system which forced astronomers to invent and combine all 3 is the same system whose strange architecture we have been tracing from the start. The difficulty of the detection is a direct consequence of the difficulty of the place. So the ledger we are about to total is not a closed book. It is a snapshot of a search still in motion, with a relook at the disappearing candidate planned for the bright yellow star, a purpose-built telescope being assembled to hunt for rocky worlds the existing instruments cannot reach, and steadily tightening limits on what can still be hiding around the red dwarf. Some of the question marks in the ledger may turn into confirmed worlds within a few years. Some may turn into firm absences, fences drawn, possibilities closed. Either outcome is knowledge. What we can say now, honestly, is that the nearest system to our own is finally being interrogated with instruments equal to its difficulty, after decades in which the questions outran the tools. The answers are coming. They are simply not all here yet. Step back now and hear the full ledger of the system, with every label in its proper place, because this is the honest map of what orbits Alpha Centauri. Around the faint red dwarf, Proxima, 2 confirmed planets, B and D. B, an Earth-mass world in the habitable zone but battered by flares. D, a confirmed sub-Earth too hot to be temperate. And a third, former candidate, C, now effectively refuted by the latest and best observations. Around the bright yellow sun-like star, 0 confirmed planets, but 1 extraordinary candidate, a possible Saturn mass gas giant in the habitable zone, glimpsed and lost and awaiting a decisive look in 2026. And around the orange star, the cooler companion, no confirmed planets, no surviving candidate, and 1 famous overturned claim, the ghost world of 2012 that was announced, celebrated, and then erased, its warm island still empty. As far as our instruments can honestly confirm, its glare-soaked neighbourhood having already produced 1 planet that dissolved under scrutiny and not yet yielded one that holds. Look at how uneven that map is, and how completely it inverts the naive expectation. The confirmed worlds cluster around the least glamorous star, the dim, distant ember that most people forget is even part of the system. The grand sun-like stars, the ones the name actually points to, the ones that look most like home, have so far yielded only a single flickering maybe, and an empty silence. The system has handed us proof in the place we least expected it, and withheld it in the place we most wanted it. That is not the symmetrical, second solar system picture the single name implies. It is lopsided, surprising, and still being written. And this uneven ledger forces the question that no list of planets can answer on its own. We have now established, as honestly as the evidence allows, where worlds exist and where they only might. The confirmed family around the red ember, the haunting candidate around the yellow sun, the unproven quiet around the orange one. But knowing that planets are there, even pinning down their masses and their orbits, is not the same as grasping what this place would actually be. Numbers on a ledger do not convey what it would mean to stand inside this system, to look up at its skies, to try to travel from one of its stars to another, to send a message across its vast internal gulfs. The architecture we built at the outset and the gravitational rules we traced after it and the worlds we have just catalogued all come together into a lived reality that is stranger than any single fact about it. A reality in which, arriving at one of these 3 stars would leave you almost as far from the other 2 as you were back home. That lived reality, and what it finally tells us about the word nearest, is where we end. Imagine you have done the impossible. You have crossed the gulf between our sun and its nearest neighbour, 4 light-years of almost perfect nothingness, a distance no machine humanity has ever built could hope to span in a lifetime, and you have finally arrived at Alpha Centauri. The voyage is over. You have reached the nearest star system to our own, except you have not reached the system. You have reached, at most, one of its stars. And that distinction, which sounds at first like a pedantic quibble, turns out to be the single deepest truth about this entire place. The truth that everything so far has been quietly building toward. Because in a system this large and this divided, arriving at one star does not mean you have arrived at the others. It barely means you have begun. Suppose your long crossing brings you to the yellow star, the bright sun-like one at the heart of the system, the one with the haunting candidate gas giant looping through its warm zone. You have travelled 4 light-years to get here. You step out, metaphorically, onto the doorstep of that star, and the faint red ember, Proxima, the very star that earns this system, its title as our closest neighbour, is still 13,000 astronomical units away from you. You have not reached it. You are not even close to reaching it. Let me make that remaining distance honest, now that you are standing inside the system rather than looking at it from afar. The whole journey you just completed, from the sun to the bright pair, spans roughly 4 light-years, which works out to somewhere around 250,000 astronomical units. Against that staggering crossing, the leftover hop from the bright pair out to Proxima 13,000 astronomical units amounts to about 5% of the trip you just finished. 5%. After travelling the entire interstellar distance from home, you would still have a final leg ahead of you equal to 1/20th of that whole crossing, simply to get from one part of the system to another. And 5% of 4 light-years is not a stroll. It is a distance many times larger than our entire planetary system from end to end. Reaching the bright stars leaves you with a last leg that is, by itself, an interstellar scale undertaking. The system does not deliver you to its members all at once. It makes you cross it, piece by piece, and the crossing between its pieces is enormous. This is why the casual phrase reaching Alpha Centauri is almost meaningless without a second question attached. Reaching which part? Arriving at the yellow star is a completely different achievement from arriving at the orange star beside it, which is in turn a completely different achievement from arriving at Proxima far out in the dark. They are not one destination. They are 3 destinations wearing a single name, and the gaps between them are gulfs in their own right. Nothing makes the scale of those internal gaps more vivid than measuring them in the one currency that humbles every distance: the travel time of light itself. Light is the fastest thing there is, the universal speed limit, and watching how long it takes to move between the parts of this system lays the whole architecture bare. Start small with the bright pair. Light leaving the yellow star and racing across to the orange companion crosses their separation somewhere between Saturn-distance and Pluto-distance, depending on where the 80-year orbit has carried them in a matter of a few hours. At their closest, light makes the trip in perhaps an hour and a half. At their widest, in around 5 hours. So the 2 sun-like stars, for all that they keep each other a planetary system apart, are still close enough that a beam of light can pass between them within a single working day. That is intimate, by cosmic standards. Now the leap outward to Proxima, and watch the number explode. To cross the 13,000 astronomical units from the bright pair to the faint red dwarf, light needs, not hours, but something on the order of 2.5 months, roughly 75 days of travel, at the fastest speed the universe permits. Sit with that contrast. Within the bright pair, light flits across in hours. To reach the 3rd member of the same system, the very same light must travel for the better part of 3 months. The gap from the pair to Proxima is not a little larger than the gap between A and B. It is hundreds of times larger, so vast that the fastest thing in existence takes 1/4 of a year to span it. And then, for perspective, widen the lens one more notch. Light takes a little over 4 years to travel from this whole system back to our own sun, and to cross the entire galaxy that contains all of this, the great disk of a few 100 billion stars in which Alpha Centauri and the Sun are 2 neighbouring specks. Light needs something like 100,000 years or more. So here is the ladder, rung by rung. A few hours across the bright pair, about 2.5 months out to Proxima. 4 years home to the Sun, 100,000 years across the galaxy. That ladder is the true shape of cosmic distance, and Alpha Centauri sits across its lowest, closest rungs, yet even down there, even at the very bottom of the ladder where everything is supposed to be cozy and near. The system is internally stretched across gulfs that take light months to cross. The consequences of those light times are not just poetic, they are practical, and they finish off any lingering image of Alpha Centauri as a single unified place. Picture some far future settlements scattered across the system. The 2 bright stars, only a few light hours apart, could in principle hold something resembling a conversation. Send a message from a world circling the yellow star to a world circling the orange one, and the reply could come back within a day or so. Slow but workable. A relationship is possible across a few hours of delay. But now bring Proxima into that conversation. A message sent from the bright pair to a settlement at Proxima would take about 2.5 months to arrive, and the answer another 2.5 months to return, close to half a year for a single exchange. Proxima is not a suburb of the bright stars. It is a remote outpost, cut off by months of silence, effectively living in a different world from the luminous pair. A single civilization could never knit this system together into one community. The bright heart might function as a unit. The distant ember would always be, in every meaningful sense, alone bound by gravity, yes, but isolated by the sheer time it takes for light to crawl between them. Now lift your eyes from distances and travel, and imagine simply standing within each of these 3 domains, looking up, because the skies themselves would refuse to agree with one another. From a world circling the yellow star, daylight would feel almost like home. A star so like our own sun that the colour and warmth of its light would barely register as foreign. But the orange companion would blaze somewhere in that sky as a single overwhelming spark, hundreds of times brighter than anything in our own night, brilliant enough to throw faint shadows and slowly breathing brighter and dimmer across the decades as the 80-year orbit carried it nearer and farther. From a world circling the orange star instead, the daylight would be softer and more amber, the home sun smaller and cooler, while the yellow star took over the role of the dazzling intruder, even more piercing than the orange star appears from the other side. And from a world circling distant Proxima, the two bright stars would not even separate into a pair without effort. They would hang together in the night as one fierce, beautiful double point of light, the brightest object in that planet's sky by far and yet still a star. Not a sun, giving almost no warmth, ruling nothing. 3 domains, 3 skies, 3 completely different experiences of what it means to live among these stars. They share a name, they do not share a heaven, and here is the detail that turns this from astronomy into something quieter and stranger. If you stood on any of those worlds and looked back the way you came back toward the patch of sky that holds our own sun, you would not see a blazing beacon marking home. You would see only a single, unremarkable star. From the vantage of Alpha Centauri, our sun would shine as a fairly bright point of light, tucked into the shape of a familiar constellation conspicuous enough to notice, perhaps, but in no way set apart, just one bright star among many. The star that gives us everything, every sunrise, every harvest, every warm afternoon in the whole of human history would be, from 4 light-years away, impossible to pick out as anything special at all. That single fact contains the entire humility of this story. We loom enormous to ourselves and vanish to nearly nothing across even the shortest interstellar gap. It is worth pausing on how we might ever cross such a gap, but only to see how even our boldest ideas crash against the system's internal vastness. Our existing spacecraft, the fastest objects we have ever launched, move at speeds that would take them not years but tens of thousands of years to reach Alpha Centauri. They would need something like 70 or 80,000 years to arrive. Far longer than recorded civilization has existed. There are more daring concepts. Proposals to fire gossamer-thin probes, no heavier than a chip, riding on powerful beams of light up to a fraction of light speed, reaching the system within a human lifetime of perhaps a few decades. There are dreams of relativistic travel, of ships moving fast enough that the journey would compress. But notice that every one of these schemes, even the most optimistic, delivers you to a star to one point in the system, and there it stops. A probe aimed at the bright pair does not also visit Proxima. Proxima is that extra 5% of the whole journey still beyond it. Months of light travel further into the dark. Even our wildest interstellar ambitions, were they to succeed beyond all hope, would not reach Alpha Centauri the place. They would reach one of its 3 islands and leave the others as distant as ever. The internal gulfs defeat the fantasy just as thoroughly as they defeat the practical reality. So let us assemble, finally, the full picture this journey has built, and see how far it stands from where we began. We started with a single dot in the southern sky, and a single name the nearest star, a tidy destination, a presumed second version of home. We end with something that bears almost no resemblance to that first impression. We end with 2 sun-like stars locked in a wide, eccentric 80-year embrace, swinging between Saturn-distance and Pluto-distance, each guarding a small, separate island of stable orbits, each forbidding any planet from serving both one golden, one amber, never the matched twin suns of imagination. We end with a faint red ember marooned 13,000 astronomical units beyond them, on a 500,000-year orbit, bound by a gravitational thread so long that light takes months to follow it, dynamically calm but lashed by flares, carrying the only confirmed worlds in the entire system on tight, days-long orbits around its dim red star. We end with a haunting candidate gas giant flickering in and out of view around the yellow star, glimpsed and lost and awaiting one more decisive look. We end, in short, not with a place but with a territory immense, divided, internally inconsistent, 3 radically different realms that happen to be chained together and happen to share a label. And this, at last, is what the word nearest truly conceals. Alpha Centauri is near only when it is measured against the rest of the galaxy. Set it beside the 100,000 light-years of the Milky Way, beside the tens of thousands of years light needs to cross from one edge of our star city to the other, beside the journey inward to the galaxy's distant heart where the central black hole, Sagittarius IE star, anchors the whole slow rotation. Set it beside all of that. And yes, 4 light-years is a whisper, the closest of all the few hundred billion stellar systems sharing our galaxy. It is the nearest port in an ocean so wide that the next nearest ports are scarcely different in their remoteness. Against that backdrop, Alpha Centauri is practically next door, but near, here, is a statement about the gap between systems, never a statement about the systems themselves. The closeness is all on the outside. Step within, and the nearness evaporates. The single nearest neighbour we possess is not a single anything. It is a sprawling 3-part structure whose own members are separated by gulfs that take light months to cross, whose 3 stars almost never share a sky as equals, whose 3 domains demand to be reached one at a time across distances that defeat even our most extravagant dreams of travel. The compression of one name into one dot is a trick of perspective, and nothing more the same trick that lets 2 stars a planetary system apart blur into a single point to the naked eye, the same trick that lets a faint ember, a fifth of a light-year out of place, be folded into the same casual label as the brilliant pair it circles. From Earth, the components blur together, and we mistake the blur for unity. There is no unity. There is only distance, wearing a disguise. That is the realization worth carrying away from all of this, and it is a sobering one, not a triumphant one. We did not find a confirmed second Earth waiting around the yellow star. We found a possible gas giant that, if real, may have swept the warm zone clean of any such world. We did not find a system poised for imminent settlement. We found a place so internally vast that arriving at one of its stars would leave us nearly as far from the others as we were back home, with months of light lag isolating its parts and millennia of travel separating it from us. We did not find a compact little copy of our own orderly solar system. We found 3 competing experiments in how to exist among stars, run side by side under one misleading word, 2 of them still largely silent, the third confirmed but harsh, and all of them divided by emptiness. And perhaps that is the most important thing the nearest star system has to teach us. If even our single closest neighbour, the very next system out, the one we name in a single breath, turns out to be this enormous, this fractured, this full of separate and radically different worlds, then the casual map we carry in our heads is wrong at its very first step. The galaxy is not a scattering of tidy points, each a place we might one day simply go. It is a scattering of vast divided territories, every one of them larger and stranger inside than its name admits, every one of them an archipelago rather than an island. The lesson of Alpha Centauri is not that the stars are close. It is that closeness itself at this scale is an illusion that even our nearest neighbour is not one destination we might reach, but an immense and broken country of 3 suns, 3 skies, and 3 separate silences, holding itself together across distances that the fastest light in the universe still needs months to cross. We reached for the nearest thing in the sky and found, hidden inside a single word, a whole divided world.